So first of all, our goal is to make a linear switch, right? And as of now, let us say we have the NMOS switch. Why is that NMOS switch non-linear? Huh? Yeah, the R-on was a function of the input voltage. This was the main issue. Now let's try to see why is this happening. Let's look at the expression again. Why my input came in the R-on expression? Yeah, this is happening because in this term there is a dependence on Vin, and particularly it is VGS, correct? So the issue is because my VGS is also some function of the input voltage. This is the main reason, right? So if I were to make a linear switch, how should this on resistance be with respect to input? It should not depend, which means it should be a constant. Fine. If I change the input, it should not change. If my on resistance has to be constant, what can you say about VGS? That also has to be constant. This is the cause, this is the effect, right? To address the effect, you go and address the cause. That is one of problem solving. So you fix this and try to make this to be constant. And let us say we are looking at an NMOS switch. You want the VGS to be constant. So you want to have a small value for VGS or a large value for VGS. To turn the switch on, you want to have a larger VGS or a smaller VGS? As large as possible. So the constant large value, what do you choose it to be? The supply we have, maximum you can. Fine. So if I can come up with a switch wherein the gate to source voltage is constant, equal to the supply, that's the best thing you can do, then our problem is solved. That is expressing my solution in words. And that is the first step you do whenever you solve a problem. Once you have in English, you can translate that English to circuits or anything you want. Program, coding, anything, right? So first let's see, when the switch is off, we don't have issues. Again, I'll take NMOS. So to turn the switch off, what do I do to the gate? To turn it off, I ground it. Here there is no issues, right? So this is no brainer. But when I turn it on, normally I was doing this. This is Vin, so this was also approximately Vin. This is what I was doing before, which means the VGS is not constant. So if my VGS has to be equal to VDD, what should the gate voltage be? VDD plus Vin. So now tell me, I need to generate VDD plus Vin. Fine. I have Vin. How do I generate VDD plus Vin? You short these two. No, I mean, yeah, let's say you can use all ideal things as possible in the world, right? Again, you start with solution, and implement it, don't worry about practicalities. Assume everything is ideal. If you put a battery or a voltage source with that value, you are set. So I will do that. Make some space maybe. Huh? Yeah, hold on. Let's see. When it is on, this is what I want it to be. Fine. Then this will be VDD plus V. Fine. But of course, this is not practical because you can't say to a customer that for every switch you put a Duracell battery and connect it, right? That is definitely not going to sell anything. So you have to have it on chip. We don't have a voltage source on chip. What is the next best thing you have? Capacitor charged to a particular voltage, acts like a voltage source, provided you don't draw a lot of current from it, right? So that's what you do. Let me redraw this here. Down. So when it is on, I want it to be like this. I have this and put a capacitor charged to VDD. So then this will be VDD plus V. Okay. Now you can't expect that I charge the capacitor to VDD once and hope that it retains a charge throughout, right? Because there will be some stray capacitance everywhere. They will start to steal some charge. So over time, the voltage across the capacitor is going to drop. So what is the fix for that? You keep losing it. I mean, you eat, you lose energy. What do you do? Eat again. Same thing. Capacitor is becoming hungry. You recharge it again. But when the switch is on, the capacitor is used like this. So when can I charge the capacitor? When it is off. I am not doing anything to the capacitor. Then I will say, right? So this is what I want. So this is the configuration I want when the switch is on and when the switch is off. Where did the copy go? I can't copy it. We'll come to that. Where is the copy option? This thing keeps changing. Okay, what do? Microsoft guys are okay. Fine. Let me draw this here. When it is off, I'll draw it here. So when it is off, I want it like this. Gate is grounded, capacitor is charged. When it is on, I want my capacitor to be put like this. So let's try to draw the overall thing. So this is the main sampling switch. When the switch is off when phi equal to 0, mind you, and when it is on, phi is 1. When it is off, I want to pull this to ground. So what do I put between this and ground? I should put a switch, and it should be controlled by which clock? Yeah, phi equal to 0. So let me draw this. Hold on. Yeah, let's not go to what switch comes there. Tell me the control signal. Fine. This takes care of this. Similarly, the capacitor has to be charged. So I'll go and put a switch. Again, this should also be clocked at 5 bar. Fine. Now when the switch is on, I want the capacitor to be put across this. What do? I need to put another switch. So we need 2 more switches. This will connect at the gate. This will connect at this terminal. And you clock it at 5. Now you see that when phi is on, the capacitor is put across the MOSFET, so that if this is V in, this becomes VDD plus V. Clear? Cool. So now that brings back to the question he was thinking. We started off with the goal of making 1 switch. Looks like in that process we are needing 5 more switches. So let us see if we are going round and round in circles, or if there is a coherent solution to this. Again, see, anything you try to come up with something new, you'll have something like this, but it's okay. You'll see as and when it's needed. I cannot copy paste this. Okay, I'll just change it here itself. Okay, so I'll erase it. Cool. So let's start to see. Let me actually label the switches, or let's start with this switch. This switch is basically trying to pass ground to my gate. What kind of switch can I use here? NMOS. As of now, we know only 3 candidates: NMOS, PMOS, CMOS. So here it looks like NMOS is a good candidate because it's passing a constant low signal. Fine. Similarly, let's look at, let me maybe say this S1, S2, S3, S4. Look at S3, that is also trying to pull this node to ground. What will I use? Clock that 5 bar. Okay. So let me label these things V1, V2, and V3. Which one? Okay, you are saying source should be here. Okay, please remember, for a transistor, source and drain are symmetric. They can be interchanged. For an NMOS, the potential with the lower terminal will be source. For a PMOS, the terminal with the higher potential will be source. That's all. This is just a, it doesn't matter what I mark. But if it's bothering, I can change it. Right? Now let me copy paste it maybe. This copy works. Yes. Yeah, so now let's look at this switch S2. When S2 is on, phi is 1. I am looking at this fellow. So what is it trying to do? When it is on, it is trying to pass V1 to V3. Fine. And what is the value V1 can take? VDD plus Vin. Right? V1 can take VDD plus Vin, which can go all the way to VDD. Fine. So I have something that is trying to pass, within quotes, a high signal. What kind of switch I can use here? PMOS. So that's the best thing we have. So let's use it. And remember, the switch is clocked at 5. So for the PMOS, the control must be 5 bar. Okay. Erase it and this. So typically, whenever the switch is seeing signals that is greater than VDD or less than 0, you ensure that both during on and off phases it works fine. So in the on phase it is okay, because to turn it on we apply 0 at the gate. So if I draw that PMOS, this is 0 volts and this is, let us say, around 2 VDD, it will turn on, no issues. Similarly, let's also make sure what happens when it is off. When it is off, phi is 0. So which means V1 will be connected to VDD. Fine. V1 is connected to VDD. So if I draw the PMOS switch, this is connected to VDD. Gate is also at VDD. So the switch will be off, no issues. Just double checking things. Is that fine? So remaining we have 2 more. Let's do that. Now let's look at S4. So S4, when S4 is on, that is when phi is 1, it is trying to pass V in here, right? Now is there some other switch in the circuit that is trying to pass V in? Huh? The main switch is also doing the same job. Here I am using NMOS for this, so what do you think I can use here? So I mean, there is not a lot of deep thought put to that, but sometimes simple thoughts work. But again, the control signal is a thing, because to turn it on, if we just give VDD, my source voltage will be at Vin. This will not be enough. So my gate voltage should actually go to VDD plus Vin, right? So let's see, when phi is 1, this is what you want. When phi equal to 0, you want the gate to be at 0. In this circuit, is there some other node that is doing the same thing? V? This gate, we are already doing that. So what can I do? I'll just connect it, because this already we are ensuring through this connection. So I can directly go and use this. The problem is solved. Okay. So that leaves with only one switch. Only S1 is pending. So let me look at S1. So S1, when it is on, the clock phi is 1 or 0? 0. Okay, this is clocked at 5 bar. So let's see, it is trying to pass VDD to V1. It's a high signal. What switch? PMOS. So it's 5 bar. For PMOS it will become 5. So again, recollect here the voltage is this V1 can go more than VDD. So we'll try to make sure if the switch works in both on and off state, right? When it is on, if I draw this, gate will be at 0. This is at VDD. The switch turns on, no issues. Let's also see what happens when it is off. When it is off, phi is 1. To turn it off, what will I apply at the gate? I apply VDD. This side is also at VDD, no worries. But this side is connected to V1. And V1, when phi is high, is connected like this. So what will this go to? This will be at VDD plus Vin, right? Because that is what is controlling the gate here. So this is going to VDD plus Vin. And this can go as high as 2 VDD, right? So what will happen to this transistor now? It will be on or off? This will be on because now this terminal is at a higher potential. So that will now act like a source and the switch will start conducting. You want this to be off, but you find that because voltages are greater than my supply, the switch turns on. Fine. So this is to turn it off. I no longer can apply VDD. What should I apply? I should be applying VDD plus Vn. So again, same thing. So you see, when phi equal to 1, I want VDD plus Vn. When phi is 0, I want 0. Which node is doing that? This guy. So what do? Yeah. If your friend has a chocolate, you want chocolate? Go and take it from your friend. This fine? So this is, I can't copy paste it. So this is the final switch, and remember the main sampling switch is the NMOS in white. The remaining colorful things are all supporting artists to make sure the entire thing functions. And like I say, anytime you come up with something new, what is the first thing you should do? You should give it a name. Some of you know. So okay. So if you had come up with this, you could have given your name, but unfortunately no. So this is called the gate bootstrapped switch. Okay, you should now depends on what this is doing, right? So this switch is trying to charge this capacitor. So you choose it so that RC of this is small enough. Right? It is all finally an RC, right? You understand what will happen if the switch has an on resistance, right? For constant signals, it is going to reduce the settling speed. So you choose it appropriately. That's all. Everywhere you do the same thing. You find the effective capacitance the switch is trying to drive. And the on resistance must be such that it is able to push in that amount of current to charge this capacitor within your required time. Okay, that's all it is. So again, what is special about this gate bootstrap switch? What is it trying to achieve? It is making it, it is trying to make a linear switch by keeping R on to be constant, and that is happening by keeping VGS to be equal to VT. Right? So now we know 4 different switch candidates. Let me just write them quickly. So we have NMOS, PMOS, CMOS, and the gate bootstrap switch. I'll call it GBS. So NMOS is an excellent switch for held signals which are low. PMOS, you use it when you are dealing with constant or held signals which are close to the supply. A CMOS switch works nice for held signals, but it can take any range within 0 to VDD. And gate bootstrap switch is typically used for sampling time varying signals so that you have very good linearity. Fine. So of course we can use gate bootstrap switch for even held signals like this, but that's simply overkill, right? That, like I say, I mean, it's not like to kill a mosquito you don't buy AK-47 and come. Same thing, you can use a CMOS switch for this case also, but if you have a CMOS switch and use it when the signal is low, PMOS is anyways not active, it's a waste of resource. Cool. So hopefully now you guys have understanding of what will happen if the switch has some on resistance, and how can you choose what kind of switch depending on the signal the switch is seeing, right? So that is the first non-ideality.